When you look up at the night sky, you are not merely seeing stars. You are witnessing a vast, silent arena where time stretches far beyond anything the human mind was shaped to comprehend. And so we begin with a question that seems simple, but is in fact deeply unsettling. Can anything we have ever built truly endure the passage of 1,000,000 years? Not metaphorically, not symbolically, but physically, atom by atom, structure by structure. Does anything created by human hands have the capacity to persist in a universe governed so relentlessly by entropy? Now here is where our intuition fails us, because everything in our daily experience teaches us the opposite. On Earth nothing lasts. Metal rusts, plastic fractures, stone erodes. Entire cities collapse into dust within a few thousand years. So we form a conclusion that feels obvious. Permanence is impossible. But this conclusion, while reasonable, is built on a hidden assumption that Earth represents the natural state of matter. And this assumption is wrong. Earth is not a gentle environment. It is chemically violent. Oxygen reacts. Water dissolves. Life consumes and transforms everything it touches. What we call decay is not a universal rule. It is an accelerated process driven by a dense and dynamic environment. Now imagine removing all of that. No oxygen, no water, no biological activity, no atmosphere. What remains is not destruction. What remains is silence. And in that silence, something remarkable happens. Decay does not stop, but it slows dramatically. So dramatically that our intuition must be rebuilt from the ground up. Let us now move to a specific moment in history. The late 1970s. A time defined by geopolitical tension, limited computational power, and yet an extraordinary scientific ambition. A group of engineers and scientists set out to solve a problem that had never been solved before. How do you build a machine that can escape the gravitational influence of the sun and continue traveling into interstellar space? The answer to that question became Voyager 1. Now we must be precise. Voyager 1 was not designed to last 1,000,000 years. It was built for a mission measured in decades. Its instruments were engineered with finite lifetimes. Its power source was always destined to fade. From an engineering standpoint, Voyager 1 is already approaching the end of its functional life. But here is the crucial shift in perspective. We are not asking whether Voyager 1 will continue to function. That answer is trivial. It will not. Its systems will fail. Its transmissions will cease. It will fall silent. The real question is deeper. Will it still exist? To answer that, we must strip away everything we associate with the idea of a spacecraft. Remove the concept of mission. Remove the concept of function. What remains is a physical object. A structure composed of atoms. Aluminum alloys copper, gold, silicon. And in physics, identity is not defined by purpose. It is defined by structure. Voyager 1 has already crossed a boundary that is not merely symbolic. It has passed beyond the heliopause, the region where the influence of the solar wind gives way to the interstellar medium. It is now moving through a domain where matter is almost absent. To quantify this, the density of particles in interstellar space is roughly 1 atom per cubic centimeter. Compare that to the air around you, where there are on the order of 10 to the power of 19 molecules in the same volume. The difference is not small. It is astronomical. So, we arrive at a paradox. Voyager 1 is traveling through almost nothing. And it is precisely this nothingness that may allow it to persist. Let us examine the dangers of space more carefully. Because space is not perfectly empty. There are high-energy particles moving at relativistic speeds. There are microscopic grains of dust. There is radiation that can interact with matter. But the key variable is not the presence of these factors. It is their density. On Earth, your body is constantly bombarded by collisions at an unimaginable rate. Air molecules striking you, photons interacting with your skin, chemical reactions occurring continuously. Voyager 1 exists in an environment where these interactions are reduced by many orders of magnitude. It is not protected, but it is isolated. Now let us return briefly to the human story because it contains a subtle but important insight. The engineers who built Voyager 1 were not thinking in terms of 1,000,000 years. They were solving immediate problems. Stability, communication, reliability. And yet within their design they included something extraordinary. The golden record. A gold-plated copper disc carrying sounds and images from Earth, not as a conversation but as a snapshot. A frozen encoding of a civilization at a specific moment in time. The choice of gold was not artistic. It was physical. Gold is chemically inert. It resists corrosion. Even in environments where other materials degrade, gold remains stable. So, embedded within this spacecraft is a quiet recognition that it might outlast its mission, that it might become something else. Not a machine, but an artifact. Now we must remain disciplined. Voyager 1 is not indestructible. Every atom within it is subject to interaction. Cosmic rays can displace atoms from their positions. Microscopic impacts can occur. Over vast periods of time, even rare events accumulate. But here is where scale becomes subtle. 1,000,000 years feels enormous, but in astrophysics it is relatively modest. The Milky Way takes hundreds of millions of years to complete a rotation. Stars live for billions of years. So the question becomes precise. Are these sparse interactions sufficient to completely dismantle Voyager 1 within 1,000,000 years? And to answer that, we must abandon intuition entirely. We must quantify. But before we enter the mathematics, let us recognize what is truly at stake. Voyager 1 is the first object humanity has sent into interstellar space. It is the furthest extension of our physical presence. If it persists, then a fragment of human civilization will continue to exist long after every structure on Earth has vanished. Not alive, not aware, but structured. This is not poetry. This is a consequence of physics. And so the question transforms once more. Not can Voyager survive, but can structure itself resist entropy long enough to outlast its creators by orders of magnitude. In the next step of our journey, we will move into the domain where numbers replace intuition. We will calculate densities, collision rates, energy transfer at the atomic level, and we will begin to see with clarity whether Voyager 1 is destined to dissolve into randomness or persist as a silent relic across 1,000,000 years of cosmic time. We now leave behind narrative intuition. and step into the domain where physics becomes unavoidable. Because the question before us is no longer philosophical. It is quantitative. What does it actually mean for an object to exist over 1,000,000 years? To answer that, we must begin with a precise definition. In physics, an object exists if its atomic structure remains sufficiently intact over time. Not perfectly unchanged, but not completely randomized either. Existence is therefore not binary. It is a spectrum. At one extreme, perfect preservation, every atom, exactly where it began. This never happens. At the other extreme, complete disintegration, atoms dispersed into the environment, structure erased. Voyager 1 will exist somewhere between these two limits. So we must identify the processes that push it along this spectrum. The mechanisms that gradually degrade structure. Let us begin with the environment itself. Interstellar space. The temperature of this environment is approximately 2.7 Kelvin, set by the cosmic microwave background. This implies that thermal motion of atoms within Voyager 1 is minimal. Vibrations exist, but they are weak. Thermal expansion and contraction are negligible. So one of the major causes of material fatigue on Earth, thermal cycling, is almost entirely absent. Next, we consider pressure, or more precisely, the absence of it. In interstellar space, the density is roughly 1 atom per cubic centimeter, which corresponds to an almost perfect vacuum. On Earth, materials are constantly interacting with surrounding molecules. Oxygen drives oxidation. Water enables corrosion. Chemical reactions proceed continuously. Voyager 1 experiences none of this. There is no atmosphere to react with its surfaces. No liquid to dissolve its materials. No biological system to consume it. So we eliminate another major degradation mechanism: chemical decay. Now we arrive at the first truly significant factor: radiation. Interstellar space is filled with high-energy particles, primarily protons and atomic nuclei accelerated by astrophysical processes. These are what we call cosmic rays. Unlike air molecules which collide frequently but with low energy, cosmic rays are rare, but extremely energetic. When one of these particles passes through Voyager 1, it can ionize atoms, displace them from their positions, and create defects in the material structure. This process is known as radiation damage. But the flux of cosmic rays is relatively low, meaning such events occur infrequently. So instead of continuous erosion, we have discrete events, isolated disruptions accumulating slowly over time. Next, we consider mechanical impacts. Interstellar space contains microscopic dust grains, remnants of ancient stars and planetary formation processes. If Voyager 1 collides with one of these particles, even a tiny grain can carry significant kinetic energy due to its velocity. However, the probability of such collisions is extremely low. The average distance between particles is vast, and Voyager's cross-sectional area is small. So again, we encounter the same pattern: rare, but potentially significant events. Now we summarize the environment. There are no continuous chemical reactions, no atmospheric corrosion, minimal thermal stress, Instead, the dominant processes are stochastic, random, discrete interactions. Radiation hits, occasional particle impacts. On Earth, degradation is continuous. In interstellar space, degradation is probabilistic. Now we turn inward to the structure of Voyager 1. The spacecraft is composed primarily of aluminum alloys, chosen for strength and stability. Copper wiring runs throughout the system, and gold plating is used in critical components, including the golden record. Gold is chemically inert. It does not oxidize. It does not corrode, making it one of the most stable materials available. From a materials perspective, Voyager 1 is already optimized for persistence. But materials alone do not determine survival. We must consider time. 1,000,000 years is about 10 to the power of 6 years, or roughly 3.1 times 10 to the power of 13 seconds. This is the duration over which all these processes accumulate. Even extremely low rates of damage can become significant given enough time. So we must avoid the mistake of assuming that emptiness means safety. Voyager is not safe. It is simply governed by a different regime of physics. Now we introduce a key concept: cumulative damage. Each interaction, each cosmic ray hit, each microscopic impact contributes a small change, individually negligible, but collectively meaningful. This is how structure degrades over long timescales. Not through sudden destruction, but through gradual accumulation of defects. So the problem becomes precise. We must estimate the rate of these interactions and determine whether their cumulative effect over 1,000,000 years is sufficient to destroy the structural integrity of Voyager 1. And to do that, we must now move beyond qualitative reasoning into mathematics. We will calculate how far Voyager travels, how many particles it encounters, how often it is struck by radiation, and how these translate into atomic-level damage. Because only then can we answer the question with precision. Not intuition, but physics. We now move into the part of the journey where intuition is no longer sufficient, and every statement must be anchored in calculation. Because the survival of Voyager 1 over 1,000,000 years is not a matter of belief. It is a matter of rates, probabilities, and cumulative effects. Let us begin with the simplest measurable quantity: velocity. Voyager 1 is moving at approximately 17 kilometers per second relative to the Sun. This is not an arbitrary number. It is the result of gravitational interactions with the giant planets during its trajectory. Now we ask a straightforward question. How far does it travel in 1,000,000 years? We convert units carefully. 1 year contains roughly 31 million seconds. So 1,000,000 years corresponds to about 3.1 times 10 to the power of 13 seconds. Multiplying by the velocity, we obtain a distance on the order of 5 times 10 to the power of 14 kilometers. This distance is about 50 light years, meaning that after 1,000,000 years, Voyager 1 will still be within a relatively small region of our galaxy. It will not have crossed the Milky Way, and it will remain within similar interstellar conditions. Now we move to the first quantitative threat: collisions with particles. The number density of interstellar particles is about 1 atom per cubic centimeter, which corresponds to about 10 to the power of 6 atoms per cubic meter. Voyager 1 has a cross-sectional area on the order of 10 square meters. We calculate the interaction rate as density multiplied by velocity multiplied by area. This gives roughly 1.7 times 10 to the power of 11 interactions per second. At first glance, this appears catastrophic. But these are mostly collisions with single hydrogen atoms, each carrying extremely small mass and energy. Using kinetic energy, 1/2 mv squared. Each interaction carries energy on the order of 10 to the power of -19 joules. This is comparable to atomic bond energies, meaning individual collisions can disturb atoms, but not tear apart large-scale structure. When we integrate over time, multiplying this rate by the total duration, we obtain about 10 to the power of 24 interactions over 1 million years. Voyager 1 itself contains roughly 10 to the power of 28 atoms. So even over this vast time, only a small fraction of atoms are directly affected. The result is gradual atomic level disorder, not structural destruction. Now we turn to a more energetic process: cosmic radiation. These are high-energy particles traveling near the speed of light. When they pass through a material, they can displace atoms from their lattice positions, creating defects such as vacancies and interstitials. The flux is typically a few particles per square centimeter per second. Converting units, we obtain about 10,000 particles per square meter per second. Over 1 million years. Voyager 1 experiences on the order of 10 to the power of 18 such impacts, each capable of displacing many atoms, leading to perhaps 10 to the power of 21 total atomic displacements. This introduces disorder throughout the material, but again remains far below the total number of atoms. So the structure degrades, but does not disappear. Now we consider the most dramatic scenario: collision with a dust grain, a microscopic particle with mass around 10 to the power of -15 kilograms, moving at high relative velocity, can release energy on the order of 10 to the power of -7 joules upon impact. But unlike atomic collisions, this energy is concentrated in a very small, localized region. This can vaporize a tiny portion of material, leaving behind small pits or microcraters on the surface. However, probability is decisive here. The density of such grains is extremely low, and Voyager 1 presents a very small target. So the likelihood of many such impacts over 1 million years remains low. They contribute localized damage, but do not dominate the overall degradation process. Now we combine all mechanisms: continuous low-energy particle interactions, rare high-energy radiation events, and extremely rare mechanical impacts. Each contributes differently, but none is sufficient to fully dismantle the spacecraft. The correct model is cumulative. Damage grows slowly. Defects accumulate. Surfaces become pitted. Materials become increasingly disordered. But the global structure remains intact. This leads us to a precise conclusion. Voyager 1 will not remain unchanged, but it will not be destroyed. After 1 million years, it will persist as a degraded yet recognizable object, a structure still reflecting its original design. And here we uncover a deeper principle. Entropy does not act as a sudden force. It acts gradually, statistically, relentlessly. Given enough time, everything evolves. But not everything loses its identity at the same rate. Voyager 1 exists in a regime where change is slow enough that even 1 million years is insufficient to erase it. In the next step, we expand beyond the spacecraft itself. We ask where Voyager 1 will be, what it may encounter, and what it means for an artifact of intelligence to drift through the galaxy across cosmic time. Now we expand our perspective beyond the spacecraft itself, because understanding whether Voyager 1 survives is only part of the question. The deeper question is where it will be, what environment it will inhabit, and what role it plays in the vast structure of the galaxy. We begin with position. After 1 million years, Voyager 1 will have traveled roughly 50 light-years from its current location. This distance sounds immense from a human perspective, but within the Milky Way, it is almost negligible. The diameter of our galaxy is about 100,000 light-years, so Voyager 1 will have traversed only a tiny fraction of it. This means something very important. Voyager 1 will still be embedded within the same general stellar neighborhood, the same galactic disk, the same diffuse interstellar medium. It will not escape the galaxy. It will not enter intergalactic space. It remains bound to the Milky Way by gravity. But motion in the galaxy is not static. Stars themselves move. The Sun orbits the galactic center at roughly 200 kilometers per second, and Voyager 1 carries that motion with it. So, over 1 million years, both Voyager 1 and nearby stars shift positions relative to one another. The spacecraft does not simply travel in a straight line through a fixed background. It moves within a dynamic system. Now we must ask a probabilistic question. Will Voyager 1 pass near another star? The average distance between stars in our region of the galaxy is on the order of a few light-years, which might suggest that close encounters are possible. But probability depends not only on distance, but on cross-sectional area and trajectory. Voyager 1 is extremely small compared to the vast separations between stars. Even over millions of years, the chance of a direct collision with a star is effectively zero. More realistically, Voyager 1 may pass within a few light-years of another star, perhaps entering its outer gravitational influence. But even this is rare on a 1 million year timescale. So, for our purposes, Voyager 1 remains in deep interstellar space, largely undisturbed by stellar encounters. Now let us turn to one of the most profound aspects of Voyager 1, the golden record. This object is not merely symbolic. It is a physical encoding of information. Grooves etched into a gold-plated copper disk representing sound waves and images. From a physics standpoint, the question becomes, will this information survive? We must think in terms of signal integrity. The grooves on the record have finite depth and spacing. Any physical change that alters the surface at a comparable scale will degrade the information. From Act 3, we know that radiation and particle impacts will gradually introduce defects. Atoms will be displaced. Surfaces will become roughened at the microscopic level. Over 1 million years, this degradation will be measurable, but not catastrophic. The grooves will not vanish, but they may become less precise. Noise will increase. Signal clarity will decrease. So the record may still be readable in principle, but with reduced fidelity. Now we must confront an even deeper question. What is the probability that any intelligence will ever encounter it? This is not a question of engineering. It is a question of cosmic statistics. The volume of space through which Voyager 1 travels is enormous. The number of potential observers is unknown, and the cross-sectional area of the spacecraft is minuscule. So the probability of interception is extraordinarily low. Not zero, but so small that for practical purposes Voyager 1 will drift unnoticed. And this leads us to a conceptual shift. Voyager 1 is not primarily a message to be received. It is a record of existence. It does not need to be found to have meaning, because its existence itself is the statement. Now we elevate the perspective further. Voyager 1 is no longer a spacecraft. It is a trajectory through space-time. Its position changes continuously. Its structure evolves slowly. But its identity is encoded in both motion and matter. If we imagine the galaxy over millions of years, stars orning, gas clouds forming and dissipating, gravitational interactions reshaping trajectories, Voyager 1 becomes part of this system, not as an active participant, but as a passive tracer, a marker of a moment in cosmic history. And here is the key realization. Most objects in the galaxy are natural, formed by physical processes without intention. Voyager 1 is different. It is structured matter shaped by intelligence. So even as it degrades, even as its materials accumulate damage, it retains a pattern that distinguishes it from natural objects. This distinction may persist far longer than we intuitively expect, because the universe does not actively erase structure. It only gradually randomizes it. And in the low-density environment of interstellar space, that randomization proceeds slowly. So Voyager 1 becomes something rare, a long-lived artifact of intelligence, drifting through a galaxy dominated by natural processes. Now, let us step back and connect all of this. After 1 million years, Voyager 1 will still exist. Not as a functioning machine, but as a physical structure. It will have traveled tens of light years, remained within the Milky Way, avoided catastrophic collisions, and accumulated only gradual damage. The golden record will likely still be present, its information partially degraded but not erased, and the spacecraft itself will continue its silent journey, not toward a destination, but along a path defined by initial conditions and the laws of physics. In the final step of our journey, we will confront the deeper meaning of this persistence, not in a mystical sense, but in a physical one. What it tells us about entropy, about time, and about the place of human creations within the universe. We now arrive at the final step of our journey, not to introduce new equations, but to understand what the equations have already revealed. Because the question we began with was never only about a spacecraft. It was about persistence, structure, and the behavior of matter across time scales far beyond human experience. Let us restate the conclusion with precision. After 1 million years, Voyager 1 will almost certainly still exist, not as a functioning probe, not as an active machine, but as a structured arrangement of atoms, degraded, imperfect, but not erased. This is not speculation. It is the direct consequence of low interaction rates in interstellar space, combined with the stability of the materials from which it was constructed. On Earth, we are accustomed to rapid change. Everything around us is in a constant state of transformation, driven by chemistry, biology, and atmosphere. But this is not the default state of the universe. It is a special condition, a dense environment where interactions are frequent. Remove that environment, and time itself behaves differently. Not in its fundamental nature, but in how its effects accumulate. In interstellar space, change is slow, almost imperceptible, but never absent. This is the true meaning of entropy. Entropy does not guarantee rapid destruction. It guarantees eventual transformation. And the rate of that transformation depends entirely on the environment. Voyager 1 exists in a regime where entropy acts gently, where disorder grows, but at a pace so slow that even 1 million years is insufficient to fully randomize its structure. So what we are observing is not defiance of physics, but its quiet consistency. Now extend this idea further. If 1 million years is not enough to erase Voyager 1, what about 10 million? Or 100 million? Or a billion years? At some point, the cumulative effects we calculated will dominate. Atomic displacements will accumulate. Materials will lose coherence. Surfaces will erode beyond recognition. And the structure we identify as Voyager 1 will dissolve into a more random distribution of matter. But that point lies far beyond the time scale we began with, which means something remarkable. A machine built by a short-lived species on a small planet around an ordinary star can persist for time spans that exceed the entire duration of recorded human history by orders of magnitude. Not because it is indestructible, but because the universe allows it. We must not assign intention where there is none. The universe does not preserve Voyager 1. It simply does not destroy it quickly. And yet the consequence is the same. A fragment of human civilization will continue to exist long after everything we directly recognize has vanished. Cities, languages, perhaps even our species. Voyager 1 will remain, drifting silently through interstellar space, carrying within it a record, not only of who we were, but of what physics allows. Here the perspective shifts one final time. We often think of permanence as something absolute, something that resists time entirely. But physics offers a different view. Nothing is permanent. But some structures decay so slowly that for all practical purposes they endure. Voyager 1 belongs to this category. It is not eternal, but it is long-lived enough to cross the boundary between human time and cosmic time. And that boundary is where meaning changes. Because once an object persists beyond the lifetime of its creators, it is no longer just a tool. It becomes evidence. Evidence that at some point in the history of the universe, matter organized itself into a form capable of understanding the laws that govern it, and of using that understanding to leave a trace. Not a message guaranteed to be read, not a signal certain to be received, but a structure that exists, and existence itself governed by the same equations we have explored is enough. So when we return to the original question, Will Voyager 1 still exist after 1 million years? The answer is clear. Yes. Not unchanged. Not intact in every detail, but unmistakably present. A silent object moving through the galaxy, shaped by human hands, and slowly reshaped by the universe. And perhaps that is the most honest conclusion physics allows us to reach. We do not build things that last forever. But under the right conditions, we can build things that last far longer than ourselves. Thank you for taking this journey together, for following the equations, for questioning intuition, and for looking at the universe not as a collection of mysteries, but as a system that can be understood step by step through the language of physics.